Hey guys, Andy here. We're back again with part 2 in this 3-part series on Gauge R&R. If you haven't checked it out, the first video was all about those key terms: repeatability, reproducibility, accuracy, and precision. If you haven't checked that out, I'll put a link in the description below. Today's video is all about the average and range method. How do you design this experiment? How do you collect data? How do you make those calculations for important concepts like repeatability and reproducibility and total Gauge R&R? All right, let's head over to the computer and get started.
All right, let's go ahead and jump in and get started. So again, I love to start big picture. If you're preparing for the Greenbelt exam, Gauge R&R or measurement system analysis is a big part of the measure phase of the body of knowledge. That same comment is true for the Black Belt exam and it's true for the CQ exam. Gauge R&R and measurement system analysis is a really important topic on all 3 exams, which is why I wanted to cover it here for you today. And then in terms of big picture, so this is actually the second part in a 3-part series. The first part was all about the basic terms and concepts in Gauge R&R. Again, I'll link to that in the description below if you want to start there. Check that out. Make sure you're very familiar with the terms repeatability, reproducibility, and what all that means, because today's lecture is all about the average and range method and how we actually calculate those really important concepts like Gauge R&R, repeatability, reproducibility, total variation, all those important calculations. In fact, throughout the video, by the way, I'm going to be referencing the spreadsheet that you can use to actually do a Gauge R&R. If you want that spreadsheet, check the link in the description below where you can get that spreadsheet for free. And then the third part in the video series is all about interpreting your results. It's not enough to make those calculations. You have to do some analysis to actually come to that conclusion and as to whether or not your measurement system is actually capable for its intended purpose. And let's jump into today's lecture. Again, I always love to start with a refresher. Remember, your measurement systems have variation just like every other process. And when you're a black belt, it's not enough to focus on, you know, the turning machine, the drilling machine, the molding machines, welding machines, whatever. You also have to think about and consider how your measurement systems are introducing variation into your data set, into your measurements, whatever. And so again, the example I gave you in lecture number 1 is you've got all this data, you run a study, you've got all this data, you calculate total variation, and you have to remember that part of your variation, and hopefully the majority of it, comes to you from your process, but also some of that variation will come from your measurement systems. And that's the purpose of a Gauge R&R. We want to quantify the variation that comes to us from our measurement systems. And again, the interpretation or the ultimate goal here is to determine whether or not our measurement systems are capable for its intended purpose. Are we using the right measurement system? Because the right measurement system will have very small measurement system variation, okay? This value, this measurement system variation, will be small relative to one of 2 things, either the design tolerance or the process tolerance. Now, interpreting your Gauge R&R value is out of scope for today's lecture. We'll talk about that tomorrow. But for today, I want to actually show you how you would conduct a Gauge R&R. So the most common method here is called the average and range method. And so I want to show you how you would design this, how you would set it up. In fact, if you want to do a Gauge R&R, I'll put this worksheet in the course so that you can leave this lecture tomorrow or today and go do a Gauge R&R for yourself and see what this looks like. But generally, the best practices here is we usually have 3 operators. And so if you look at this spreadsheet, if you look at this little data sheet or whatever, the far left-hand column is appraiser. A, B, and C. That's our 3 operators. The other thing that you're going to notice that we do is we're gonna measure 10 different parts. Now, something that's really important to know here or to think about here when you're selecting these parts is you must pick samples that span your entire design tolerance and your entire process tolerance. And I'll come back to this point here when we talk about part-to-part variation and making conclusions and explain why this is so important. But just know for now that when you pick these samples, you should pick 10 parts that span your entire design tolerance. The other thing that's really, really important, and we talked about this when we discussed repeatability, is for every sample that you measure for every appraiser, you're going to take what are called replicate measurements. You're going to measure each sample multiple times, 1, 2, and 3, and we'll come back to that when we talk about repeatability and inherent equipment variation, things like that. You want to make sure each operator is measuring the parts multiple times. Before I show you the calculation, though, I want to explain something. When we talked about repeatability and reproducibility and even Gauge R&R, those were always reflected or measured as or reported as a measure of standard deviation, a sigma value, okay? And I want to help you make the connection. We call this the average and range method. And I remember when I was new to this idea, I remember thinking, why do we calculate a range value if what we care about is standard deviation? And so I want to show you this equation here because this is essentially the conversion between range and standard deviation. We use what are called D2 factors. If you have a range value and you divide by a D2 factor, you can convert that into an estimate of standard deviation. And we're actually going to do this multiple times. Let me show you all the calculations. So the two big ones are repeatability and reproducibility, and you can see here how each of those equations requires the usage of a D2 factor. I will say that D2 factor is probably the most difficult part of a Gauge R&R because it changes depending on how many samples you use or how many operators or replicate measurements. It can be kind of tricky to pick the right D2 factor given your circumstances. Also remember that when in the very first lecture when we talked about repeatability and reproducibility, we're eventually going to add those two things together to calculate Gauge R&R, your measurement system variation. Your Gauge R&R is equal to your repeatability plus your reproducibility. And so that's going to be one of the equations that we walk through today. We'll calculate Gauge R&R by essentially taking the square root of EV squared plus AV squared, and I'll show you how to take a data set and calculate Gauge R&R. Now, that's not enough. Remember, it's not enough just to calculate a Gauge R&R value and go, boop, we did it, we have a number, we executed the experiment, whatever, we're good. At the end of the day, your Gauge R&R value, right, for a measurement system to be capable, that Gauge R&R value should be small relative to your design tolerance or your process variation, okay? Now, next to the word process variation, I've added a new term here. I've added this term part-to-part variation because this is actually one of the calculations that we're going to make in our Gauge R&R, okay? We're going to make this calculation. We call it part-to-part variation. Now, and I want to re-explain something that I said earlier. You want to pick parts that span your design tolerance. We do that because we want our part-to-part variation number to essentially reflect our design tolerance or our process variation, because the final calculation that we're going to make for our entire experiment is this idea of total variation. The total variation in our entire system is the variation from your measurement system plus the variation from your process or your design, whatever your design tolerance. And so again, at the end of the day, we're going to make comparisons of Gauge R&R relative to total variation. And so we want to make sure that this part-to-part variation number is accurate and that it reflects our entire design tolerance so that our analysis is ultimately correct at the end of the day. So those are the calculations we're going to make. Here's the actual spreadsheet. Let's say we're going to run our experiment. We've got 3 operators, 10 parts, 3 times. We give them the parts. We monitor their measurements, whatever. We train them on the measurement. We've got these calipers. We're measuring a diameter. And essentially, all the operators do themselves is fill out these little orange cells here, okay? That's the data entry portion. Everything else about the spreadsheet is a calculation. And now what I want to do is I want to show you how those calculations translate into repeatability, reproducibility, all the things that we care about when we talk about a Gauge R&R. So let's start with repeatability. Remember, let's go back to the definition here. Repeatability reflects the inherent variation within the measurement system itself, okay? And the question becomes, how do we do that? How do we take this raw data and tease out the inherent variation within the measurement system itself? We do that by calculating a value called R double bar, okay? R double bar, you'll see it down here. R double bar is the average value of the range measured within each operator, within each part. So here's actually the data set that I showed you in lecture number 1 when we talked about repeatability. If you look at these 3 data points, you can calculate the range value associated with just these data points, right? And that range value is 1.0. It's 1.0. That range value is a reflection of the variation within an operator, right? We've got the same person measuring the same parts. This is the variation within an operator within a part. And we assume that that variation there is essentially inherent to the equipment itself, okay? And so for each of these replicate measurements, whatever, we're going to calculate a range value. And we do that 30 different times. Look at all these different range values, okay? All of these range values that we calculate essentially reflect the same thing. It all reflects the inherent variation within the measurement system itself because we've blocked out part-to-part variation, we've blocked out operator-to-operator variation. We are just quantifying the variation attributable to the gauge itself. And then what we do is we take those 30 individual range values and we calculate the average. This is called R double bar. This is the average value of the range. And for this particular experiment, on average, our inherent variation just for the gauge could be measured as 0.624 inches, okay, inches. Now remember, that's a measure of range. We want to convert that into a measure of standard deviation, okay? And this is where we get into the D2 factor. So now as an engineer or whatever, as a black belt, you have to convert R double bar into that measure of standard deviation. And when it comes to repeatability, that depends on a few different things. Here's the table you're going to use. This table comes from the AIAG Automotive Industry Action Group a measure. They've got a great Gauge R&R reference. It's probably the world-class standard for Gauge R&R. These are the D2 factors for Gauge R&R. And when you're calculating repeatability specifically, the way you look up your D2 factor is you first think about M. So M here is across the top. That's your subgroup size. That's the number of replicate measurements we took. Okay, and remember, we took 3 replicate measurements. And the N value here, which is this first row, is essentially the number of range values that we calculated our average from. So you make the calculation as the number of parts, which is 10, times the number of operators, and that comes out to 30. Remember, we averaged up 30 different range values to calculate R bar. So N is essentially that sample size. It was 30. Now, something that you need to know about this particular table, when your sample size is greater than 15 here, you get to default to what they call D2 prime, okay, D2 prime. If your value of N is ever greater than 15, which is usually true for most Gauge R&Rs, just use D2 prime, which means for us, the right D2 factor for this calculation is 1.693. You can see it there. And when we divide our R double bar by that value, we translate that range value into a measure of standard deviation, and we can calculate repeatability as 0.3688. That is how you do the calculation. Now, the next thing we need to do is to calculate reproducibility. Remember, when we talk about reproducibility, it is defined as the variation between operators. Okay, the variation between operators. And in the very first lecture, I kind of had this little graph here where we've got 3 different appraisers, and what we're doing is we're measuring the difference between their average values. Okay, and we call this difference here the operator range. Okay, we're going to find the biggest appraiser, the smallest appraiser, and we're going to find the range between our operators. So what does that mean in terms of the data set? If we go back here to the data set, what we can do for each appraiser, remember we have 3 different appraisers, we're going to calculate an average for each appraiser. So for appraiser A here, we could take the average of all 30 data points that appraiser A came up with. Then we take the average of all 30 data points from appraiser B and do the same from appraiser C. And remember, in a perfect world, these appraisers on average would all measure the same value, but clearly we know that's not true, and clearly that doesn't happen in real life. So this is how we measure the variation that comes to us between the appraisers, right? If appraiser A does it differently than appraiser B, on average, they're going to get different values. And so we can essentially quantify that using something called the operator range. We find the maximum operator average, 47.06, operator A, minus the minimum operator average, 46.28, that was appraiser C, and what we find is that the range between operators is 0.788. Now again, we have to translate that into a measure of standard deviation. Here's the equation. I've literally never seen this equation come up on any sort of ASQ exam, and so I'm going to go through this pretty quickly. When you are making this calculation, the way you look up your D2 factor changes. Your N value is always equal to 1, and your M value, your subgroup size, is always equal to the number of operators. So for us, that was for 3 operators, obviously that's 1.912. If you work this equation, essentially you can calculate the reproducibility or the appraiser variation as 0.4074. Okay. Now, once we've calculated repeatability and reproducibility, we can now quantify or calculate the Gauge R&R for this particular measurement system. And remember, here's that graph again. Gauge R&R is simply just repeatability plus reproducibility. We have to do it in the variance form. And so essentially we take the equipment variation and square it, plus the appraiser variation and square it. We take the square root of that to calculate Gauge R&R. Now, these are the numbers we just calculated. 0.3688, that was our repeatability. We square that. 0.4074. That was our reproducibility. We square that, and we can calculate our gauge R&R value to be 0.5495 inches. And I want to re-emphasize the units of measure, because remember, gauge R&R can be calculated as variance or standard deviation, and the best way to tell the difference is to simply look at the units of measure. Now, we've done it. We've calculated a value, and the next question that you have to ask yourself is that good or is that bad? Is that a lot of variation, or is it too much variation, or is it the right amount? Now we have to actually make that assessment, and I keep coming back to this phrase: for your measurement system to be capable, your measurement system variation, this gauge R&R value, should be small relative to either your design tolerance or your process variation. Okay, so let's now calculate our process variation. Let's now calculate part-to-part variation. Okay, and here's let's actually go to the data, and I'll show you exactly how we do this and why it matters. So if you look at the data here, okay, look at sample number 2. We ended up taking nine measurements for sample number 2. Down here in this very bottom row, we call this part averages. This row essentially takes an average of all 9 measurements associated with part number 2, and it calculates an overall average for each individual part. The same thing is true for every sample: 1, 2, 3, 4, 5, 6, 7, and 8. I'm showing you these two specifically because they're the smallest and the largest sample in this experiment. And I want to use this to actually re-emphasize this piece of advice I gave you earlier. When you're picking these 10 samples, you must pick parts that span your design tolerance, because it factors into this part-to-part variation calculation, okay? And so again, this row down here shows you all of the average values for each individual sample themselves. And once we have these part averages, we can calculate our part-to-part variation. So here's the equation. Part-to-part variation is essentially the range between the parts. What is the range between the parts divided by that D2 factor? So the part range is simply just the maximum part size, 50.95, minus the minimum part size, which was 41.31, giving us an overall part range of about 9 inches, 9.6535 inches. That's the part range. And we can translate that into a measure of standard deviation by dividing by the D2 factor, 3.1791, okay? Now again, here's how you look up that D2 factor. Again, for the part-to-part variation, the approach you use is different. So here we always use n equal to 1. That's this very top row, and m equals the number of parts. And that's actually off the chart. So we use 10 parts. You'd have to go out here to subgroup size of 10, but I put it here on the slide. So D2 is equal to if you use 5 samples, D2 is equal to 2.48. If you use 10 samples like we did, our D2 factor is 3.1791, which again is what we included here. This is how you calculate part-to-part variation. Now, the final calculation we have to make, and I know we're running long here, is all about total variation. What is the total variation in our experiment? And remember, that's simply just your part-to-part variation or your process variation combined with any measurement variation that you had from your measurement system. And that's the calculation we get to make next, okay? This is total variation. And again, I'm showing you the whole diagram, right? We've got total variation, process variation, gauge R&R in its component parts, repeatability and reproducibility. And here's that equation. Total variation is equal to the square root of your gauge R&R squared plus your part-to-part variation squared equals a total variation of 3.0802. And that is the final calculation for today's lecture. And the question still remains, is our measurement still capable of meeting our intended needs? And that's going to be the third part in the video series. We're going to take these results. We're going to do some calculations, the precision tolerance ratio and the percent of total process variation, to essentially make that conclusion. Is our measurement system capable of its intended purpose? And then, like I mentioned earlier, there's a free resource you can get. Go to greenbeltacademy.com/GaugeR&R to get that Excel template. It'll do all those calculations for you in terms of repeatability, reproducibility, and even the precision tolerance ratio. All those calculations associated with the average and range method are handled through that spreadsheet. The other thing that I love to share is this free course. You can go to greenbeltacademy.com/free course, and I'm going to cover a bunch of different topics that are important to the Greenbelt exam: to make lean, design for Six Sigma, the 7 QC tools, process capability, the normal distribution. There's going to be a bunch of video lectures, practice exams, a bunch of stuff to help you prepare for the Greenbelt exam, so head on over. Also, if you like this video, do me a favor, hit the like button. That way other people who are on this Greenbelt journey can find the same content and grow and learn. And then if you're ready to really get serious about the journey, hit that subscribe button. That way, as I publish new videos or the third part in the series, you get notified and you can continue learning and growing. All right, that's it for me. Thanks so much. Have a good one. Bye.